Here's the Wigner-Eckart theorem, which expresses matrix elements in terms of Clebsch-Gordon coefficients and then these so-called reduced matrix elements. And now the first question is, what does this reduced matrix element really depend on? So let's just erase this. If you look at this equation down here, then you see that apparently it does depend on alpha, it does depend on lambda, so that shows up here, the lambda. It does not depend, the reduced matrix element does not depend on I, j, and L. So which individual basis vector you're just using, it doesn't depend on that. It's more a statement about which irrep is involved. And now you might wonder whether it does depend on mu and nu, these irreps. And well, it does, because what we're doing here with these Clebsch-Gordon coefficients, there's a change of basis. So we start with, say, this E nu j, and then we apply the O mu I operators, and then we do a basis change to these W, where did we put the indices, lambda, alpha case. So this basis change really depends on what we start from, and that's where the mu and nu dependence comes from. So that's really there. Now, why is this Wigner-Eckart theorem useful? Well, if you look at it, then you see that there are potentially many matrix elements here on the left hand side, which are expressed in terms of a couple, well, also maybe many Clebsch-Gordon coefficients, but only a smaller number of so-called reduced matrix elements. So the idea is that if this is some application, maybe some physics application, then all the physics is in this reduced matrix element. And here the Clebsch-Gordon coefficients, that's just some representation theory. So many matrix elements here are fixed by a few reduced matrix elements, and then some information on the representation theory that's involved here. And now, how do you actually use this Wigner-Eckart theorem in an explicit problem? Well, you would determine a couple of matrix elements, then you know all the Clebsch-Gordon coefficients, and then you view the Wigner-Eckart theorem as a linear system for the reduced matrix elements. So you determine by some means a couple of matrix elements. From these you get the reduced matrix elements, and then you know all the matrix elements.